good time. So it is a really great pleasure to introduce Professor Andy Strominger. Especially this is a really extremely wonderful opportunity for me, especially because I was Andy's postdoc actually 20 years ago at Harvard and really enjoyed the group, Andy's group, and also really learned quite a lot of things from Andy. So Professor Andy got his PhD at the MIT in 1982, and he became a long-term member at the IS in Princeton. In 1986, he became a professor of physics at UCSB, and in 1987, Andy moved to Harvard, and he has been a Grill York professor of physics until now. As you know, Andy has made a tremendous contribution to the subjects of quantum gravity and string theory and related topics, and such as a microscopic derivation of black hole entropy from string theory, and also discovery of this DSCFT, for which we will hear more in this colloquium, and the Calabial compactification, many great accomplishments. And he has been awarded also, of course, quite many prestigious prizes, including Breakthrough Prize in Fundamental Physics, Prime Medal, Dirac Medal, and so many wonderful prizes. So, okay, so it's a so let us invite Andy to give a colloquium. His title of his colloquium is Cosmic ER EPR. Please, Andy, start.
Okay, well, thank you. It's my honor to be invited to give the Extreme Universe colloquium. And thank you all for staying up. I hope you had a nice dinner and can enjoy this as after dinner speech. And please feel free to ask questions anytime during the talk. If you could just blurt them out. And that, of course, always helps me know how people are following. So I'm going to talk today about a recent paper, Cosmic ER, which is Einstein-Rosen equals Einstein-Podolsky-Rosen in the DSCFT correspondence. And it's a paper that I wrote with Jordan Kotler just a month or two. So the holographic principle, roughly speaking, this talk aims at understanding the holographic principle in a general setting. And roughly speaking, and there is no precise formulation of the holographic principle, it posits that a bulk quantum theory of gravity has a dual representation as a quantum theory without gravity, which lives on the boundary of the space-time in question. And in some cases, now there's one case which we understand very well now, I think it's fair to say, and that's an anti-de Sitter space. And in some cases, one can see rather explicitly the emergence of space-time coming from the structure of quantum correlations between different points, different subsets of the conformal field theory that lives on the boundary of ADS space. And perhaps one of the best examples of this, which in part leads to the slogan ER equals EPR, comes from the ADS Schwarzschild diagram. So here we have a Penrose diagram of the ADS Schwarzschild geometry. And this line here is, say, if we were doing ADS4 to be in 4 dimensions, this line here would be each point on it. This is the boundary of an ADS geometry. Each point on it would be an S2. There would be an S2 here. And then here we have in the middle a black hole, which has a wormhole connecting the two regions This is the Einstein-Rosen bridge. And then there's a second asymptotic region. So this is just like the structure of ADS, of the Schwarzschild solution in Minkowski space, except that in Minkowski space, instead the infinity, the spatial infinity, instead of being a circle, a sphere times time, would just be, there would be past and future null infinity. Now we want to think about the quantum theory on this background. And in the quantum theory on this background, one thing we might do is we might define the quantum vacuum here by demanding that that the vacuum is annihilated by positive frequency modes with respect to Schwarzschild time. That vacuum is not the usual Hartle-Hawking vacuum. It's the Bowler vacuum. And it has an infinite Casimir energy at the boundary. There are no particle presence, no thermal radiation. And that could certainly be represented as a state so in that state, if we compute correlation functions here, we put an operator here in one side of the wormhole and one on the other side of the wormhole, the correlation functions vanish. Even if you put them very close here, two scalar field operators in the Bowler vacuum, there'll be no correlations between them. It's much like the Rindler vacuum. It's the analog of the Rindler vacuum in Minkowski space. So really, in effect, these two exterior regions are completely disconnected. And this region would be holographically dual to this. This is the domain of causal dependence of the boundary. And it would, everything that you would compute in such a vacuum state would be totally described by the dual conformal field theory living on this boundary. And similarly over here, it would be described by the conformal field theory on this boundary. But that is not the vacuum we usually like to discuss. We usually like to discuss the Hartle-Hawking vacuum, which can be thought of as a thermal state, a thermal field double state built on, it's a pure state on this global space-like slice. And modes here are correlated with modes here. So there is a correlation function, and if you take 2 points very close together, there's a correlation between the quantum fields, which just looks just like the correlation at short distances. It has the Hadamard singularity characteristic of standard 2-point functions at short distances in quantum field theory. So that's the more natural thing to do. So we see that in that case, these two sides of the black hole talk to each other. They have correlations. And so the correlations are like those. I mean, they're different in detail, but they're like, so here I've got ER, the Einstein-Rosen bridge, and they're like the correlations in the EPR pair. They're correlations between spatially separated objects. So the statement is that when you put in the quantum correlations, then you have an Einstein-Rosen bridge, and that's the origin of the slogan, which I believe was coined by Maldacena and Susskind, that ER is equal to EPR. And if you do this, not only do you get the Einstein bridge, but you can put correlation functions anywhere around the space-time. So we can see, in a sense, that space-time is built, the causal structure of space-time is built out of quantum correlations, the structure of correlations, in this case, between the two copies of the dual conformal field theory. And now, can everything be seen okay on this blackboard?
Yeah, I think I can see that clearly.
Good, okay. Now, there are much more subtle versions of this, even a single copy, which I'm sure Tadashi has told you about, where you can take correlations of subsets of the boundary theory, and you can understand in a very beautiful way how the whole, just even in one copy of ADS, you can understand the structure of the correlation is, of course, is an entanglement between different pieces of the boundary, is encoded in the famous Ryu-Takanagi formula. And from that, you can see how quantum correlations, even in a single copy, build up the interior of the bulk spacetime from quantum correlations between sections of the boundary. Now, but that is not, I'm going to, in this talk, I'm going to be developing the analogy with this picture. But let me, before I do that, let me briefly mention, there's another example of this kind of ER equals EPR formula. It's something that we expect is not particular to anti-de Sitter space, even if anti-de Sitter space is the place where we can currently write down the most concrete formulas. And so the point of this talk is to try to start to generalize this notion of space-time arising from quantum correlations to more general settings. And one more general settings where it's already been discussed is when you have pair creation of a pair of black holes, say in a magnetic field, charged black holes, and the quantum states are correlated so that it's a pure state. And then in the corresponding, I'm not going to go through this example in detail, it's in the literature, the quantum correlations between a scalar field here and a scalar field here far away near the other black hole will become very large because of the correlations of the quantum state. So that's another case where we can see the Einstein-Rosen bridge coming from the structure of quantum correlations. So it's more general than its ADS setting, and we should use our understanding of ADS as a jumping off point to more general situations. Now, the situation I want to study in this talk, in which we can be relatively precise, is something which looks very similar, and that's going to be de Sitter space. So in de Sitter space, this is now the Penrose diagram of de Sitter space, and it looks just like this, except instead of the singularities here, I have scri plus, scri minus. These would be, I'll always be in 4 dimensions. These will be 3 spheres. Now, but instead of a 2-sphere here, you just have a point, and every point in this diagram is a 2-sphere, but they get smaller and smaller here. So all these cross sections are 3 spheres. And then we have the so-called southern and northern static patches of de Sitter space, which are causally separated region. And there you can see, obviously, I drew it this way on purpose, that it's very similar to the Schwarzschild case. And indeed, so what we're going to do in this talk is to try to use, here we used ADS CFT. Now we're going to try to use DS CFT to understand the structure of how, in fact, de Sitter spacetime itself emerges again from a thermal field double in the dual boundary conformal field theory. Okay, so let me say a few words about what DSCFT is. First of all, DSCFT is very different from ADS-CFT in several ways. The first way, which I think is often unappreciated, ADS-CFT is a top-down construction. We started with string theory, which we understand in perfect detail, and we took various limits, and we discovered that there's some exact duality between a conformal field theory and a bulk ADS spacetime. That's a top-down approach. In DS-CFT, we're not hoping to find an exact dual, because finding an exact dual is tantamount to knowing all the laws of nature. That's not what we're trying to understand now. Rather, we're saying, let's assume that the holographic principle somehow works in DS-CFT, and there might be many different ways that you could try to make it work. And what constraints can we derive on it? What structure do we know that it must have from the symmetries and the various properties of the low energy field theory? So one thing that we know, so the first, or a guess, people have guessed different things, but my guess is that, like in ADS, the dual conformal, well, first of all, the isometry group is SO4, 1. So that's the conformal group of a CFT3. And so where would the CFT3 fit? Well, you want the holographic dual to fit at the boundary, and there's an S3 up here. So it's natural to think that there would be some kind of three-dimensional CFT which lives on the boundary. And in fact, I should mention that there is one example, not in string theory, but in Vasiliev gravity, where there's an explicit construction of the CFT3. So we know that at least as a mathematical structure that it works. It's self-consistent. Now, if you take correlation functions of a scalar field in CFT in the bulk of DS, and you push them to the boundary and rescale them according to their conformal weight, as one does in ADS, you find that you can define a set of correlation functions that behave like those of a conformal field theory on the boundary. So Green's functions pushed and rescaled to the boundary give us correlation functions in the CFT3. But now what we're going to do, what's a little different than most discussions in this talk, is we're going to ask about states in the CFT3. Well, in ADS, so this is DS, in ADS, time in the boundary is the same as time in the bulk. And there's a very simple dictionary between the bulk Hilbert space and the boundary Hilbert space. They're just the same thing. That can't possibly be true in DS, because the boundary is a space-like surface with no time in it. And so where are the states? Well, so now I'm going to make a very simple observation, which has been mentioned in some papers a decade ago, but not really discussed that much. So if we have a three-dimensional CFT, the states want to live in two spheres. And so let's take an S2 that lives up on Scribe Plus. And it turns out that because of the nature of Scribe Plus, that S2 is the boundary of an everywhere space-like surface in the bulk. Therefore, we should a state on a bulk state on this space-like slice here, which is not a complete space-like slice, is identified with the state in the boundary theory on the S2 where that slice hits infinity. However, unlike in ADS, there are two ways to do this. So we could also have a bulk state over here, which would also give us a different state in the boundary CFT living at the S3 at infinity. And these two states, these two slices together are a complete space-like slice, and therefore an ordinary bulk state in the bulk Hilbert space lives in the tensor product of the boundary Hilbert space. You need two copies. So roughly speaking, H bulk is like H CFT3 squared. So now you can guess. So I'm going to be more precise about all this, but now you can guess where I'm going to going. I'm going to argue that the Hartle-Hawking state is a thermal field double state in this boundary CFT3, and that the whole space-time, the whole de Sitter space-time emerges. That one copy of the CFT3 cannot, there's no state in it that corresponds to all of de Sitter space. And you need two copies of the CFT3, and then you have a thermal field double. So where I'm going is that the basic usual Euclidean vacuum in de Sitter space is more like this, it's a kind of analog of the thermal field double black hole state in ADS than it is like the ADS vacuum. There isn't really an analog of the ADS vacuum in DSCFT.
Sorry,
okay.
Andy, I have a question. So this state can be constructed by some Euclidean path integral? I mean, so in the boundary, you have S3, and you are picking up S2 inside S3. And usually holography relates to some quantum field theory on S3. Then we can construct some quantum state on S2 by some path integral.
Well,
interpretation is different.
You would get, the Hartle-Hawking prescription gives you a bulk state on S3 by a path integral in the bulk quantum gravity. And that's a particular state in the bulk Hilbert space, but we're allowing for any state in the bulk Hilbert space. We're not insisting on the Hartle-Hawking vacuum.
But also, it can relate to some CFT, I mean, boundary theory. And boundary theory is defined on S3. Time like infinity is S3.
Yeah.
And can we relate to some path integral on S3?
A path integral on S3. We might be able to do something like that. Right. So we had a different description of this, which we didn't fully work out. It's at the very end of our paper, where you could also describe this as a disordered average of a path integral with sources. I mean, if you don't have path integral without sources, it's just a number. So that's not very much information. But you could have a generating function on this S3 and a generating function on this S3. And then this all can be described as a sort of disorder average of the product of those two generating functions. That's a different picture, probably equivalent in some way. We hinted at that in the last section of our paper, but it isn't what I'm doing now. What I'm doing now is I'm thinking about any state in the bulk, not just the Euclidean vacuum. You need two copies of the boundary CFT to write it. Just like any state on the global in ADS, if you have the ADS Schwarzschild, you need two copies of the CFT. In using two copies of the CFT, any state, any nice smooth state can be written in that tensor product space. The vacuum, the Hartle-Hawking vacuum, is a particular one. It's the thermal field double, but more general states can also be written. And
thank you very much.
yeah. Okay. So now to get this all to, so that's the basic idea. And the thing that we're going to learn, whereas in ADS, we found that the Einstein-Rosen bridge and the interior of the black holes arises from the quantum entanglement. What's interesting about the DS case is that the whole space-time arises from the whole universe arises from the quantum entanglement. Okay, so now to make this all very precise, it's important to go into. So about 10 years ago, there was a series of papers by Hosoya and Yamamoto, and then myself and Jimseng Ing and Moldesina and Pimental, kind of dividing de Sitter space in half in various ways and looking at quantum entanglement and so on, using a different basis. And it turns out that there's a very nice basis which makes the problem very easy, and it's a very physical basis. It's the basis of quasi-normal modes. Now, and these were shown to be complete about 10 years ago by Jaffris, Ing, Lipsowska, and I. So, for example, black holes, you're used to quasi-normal modes of black holes. They are not a complete basis. So quasi-normal modes, of course, have imaginary frequencies. They represent ring downs. They describe, roughly speaking, perturbations in the vicinity of the black hole. But if you have a black hole in flat space, you need to augment it by plane waves passing by far away. Those are not part of the quasi-normal modes. But it turns out that in de Sitter space, the quasi-normal modes do form a complete basis. And importantly for our purposes, they fall into nice SO4,1 representations. So everything becomes really easy. Okay, so let's take, let me set the de Sitter length to 1. And let's take the de Sitter metric, dt squared plus cos squared t d psi squared plus sine squared theta. Just going to write out this explicitly. Sine squared psi d theta squared plus sine squared theta d phi squared. This is probably the most familiar form of the de Sitter. We have a time. It's not a killing var. There's a cos t here. Here we have a 3-sphere, which reaches a minimum at t equals 0 and t equals 0, and it expands to the past and to the future. And then we have a scalar field theory. We're just going to study a massive scalar field. And then we have 2 classes of quasi-normal modes. Let me call them phi plus or minus quasi-normal, which is equal to I e to the minus I pi h plus or minus over sinh t minus cos t cosine psi, we need an I epsilon prescription, to the h plus or minus. And then we have also anti-quasi-normal modes, which are the same, except we have a plus here. And we still have the minus I epsilon. So let me draw a picture here, again, of de Sitter space. So this is a southern static patch, the northern static patch. This quasi-normal modes for either plus or minus. Oh, I need to tell you what H plus and minus are. H plus and minus are equal to 3/2. It's the conformal weight under SO41 plus or minus the square root of 9/4 minus m squared L squared. Let me put the de Sitter length back in, okay? And there's a range of masses for which H plus and minus are both real, and we avoid the integers. We're specifically talking about the range where this is real. So that's saying that the Compton wavelength is longer than the de Sitter radius, so they're very light fields. When m gets big, this becomes imaginary. I don't think this is an essential restriction, but the different cases have to be treated separately. So for now, we're just doing that. And the quasi-normal modes are singular along a line like this, but in the southern patch, they decay exponentially towards the future. The anti-quasi-normal modes, so the quasi-normal modes do this, they're singular along there, but they decay to the future. The anti-quasi-normal modes in blue decay towards the past. And quasi-normal modes and anti-quasi-normal modes are exchanged when you exchange the North Pole and the South Pole. Now, what's special about this isn't all the quasi-normal modes. What's special about these is, well, first of all, if we take L naught phi plus or minus quasi-normal, I'll tell you what L naught is in a minute. Well, I'll tell you now. So there's a killing vector, L naught, that does this, and it also does this, and then it goes backwards here, and it does this. It's a killing vector which is everywhere time-like in the southern patch. L naught phi plus or minus quasi-normal mode is equal to minus H plus or minus phi plus or minus quasi-normal mode. And if we look at the anti-quasi-normal modes, we get a minus sign there. Though, of course, if we switch north and south, we would also change L naught by a sign, so they're qualitatively similar. And where L naught is equal to I L naught is equal to I times the derivative with respect to static patch time, which is the static patch Hamiltonian. So there are lots of funny I's that must be understood when in the DSCFT story. Now, we're talking about quasi-normal modes here. So we see that if their L naught is real, then H is imaginary. And of course, quasi-normal modes have imaginary frequencies. So that's what we expect, but it's not what we usually have. And L naught, well, we can write it out explicitly in terms of these things, but maybe I won't bother with that. But in addition to the there are 9 more killing vectors their SO41 has 10 killing vectors, and their JK, which are the ordinary spatial rotations. I'm not really interested in that, but they're the boost M plus K and M minus K. There are 6 boost killing vector fields, which raise and lower L naught. And importantly, M minus K by plus or minus quasi-normal modes is equal to 0 as M plus K annihilates the anti-quasi-normal modes. So these wave functions I wrote down, now I've erased them, they're not only eigenvalues of the static patch time, they are highest weight. If we view SO41 as a conformal group of the 3-sphere, they're highest weight states of the conformal group in 3 dimensions. So they're conformal primaries, as we would say. And if we were thinking about the conformal field theory on S3, we would always work in a basis where we talk about conformal primaries and their descendants. So that's what's nice about this quasi-normal mode basis, is it matches what we would do in 3-dimensional conformal field theory. The usual global modes in de Sitter space, where you have spherical harmonics and so on and so forth, are very complicated mixtures of the kinds of representations of fields that we would use in talking about 3-dimensional conformal field theories. Okay, so and when we come to talking more about the boundary field theory, there's just a very natural map between states in the boundary field theory and quasi-normal modes and their descendants. Okay, now I want to do something else. All right, so at this point, we have 4. So now we can take all kinds of descendants. And so we consider not just these primaries, but their descendants are also quasi-normal modes. And let's B be a multi-index, which involves taking all possible descendants of the quasi-normal modes, and I guess you could say ascendants of the anti-quasi-normal modes, though if we reverse our sign of L naught, those also become descendants. So we have 4 kinds of modes now that we've discussed. We have this mode, the complex conjugate of this mode. Remember, there was an I epsilon prescription in there. And then we have 5 plus or minus anti-quasi-normal modes and 5 plus or minus anti-quasi-normal modes, complex conjugated. Okay, so what was shown in Jaffrus, Lukowski, and myself about 10 years ago is that this is actually a doubly overcomplete set of modes. There are many different ways of seeing this. One is that we can, roughly speaking, think of the plus modes as Dirichlet and the minus modes as Neumann. There's also a shadow relation between the plus and the minus modes, that they're dependent. So I'm going to henceforth, and there are different ways of taking only half of these modes, but you can see that that if I just always take the plus modes, that this is a complete basis of modes in anti-de Sitter space, and it's also the existence of 2 sets of modes is also related to duality in the boundary conformal field theory, that the boundary conformal field theory has 2 dual presentations. Anyway, so henceforth, I'm going to drop the minus modes, and I'm only going to think about the plus modes. Now, this is not quite the basis I want to use. I want to use so we see there, I just erased it, but we see that we have, when we erase the minus modes, we have 4 towers of modes. I'm going to use a different 4 towers. It turns out that real 4 towers, let's call this the south, let's call this the north, and let's call this the future, and let's call this the past. So it turns out that we can, by a judicious combination of those 4 sets of modes, we can find one set of modes with support here, which I'll call phi fs. And we could have another set of modes with support here, which I'll call phi ps. And then another set of modes here, which I'll call phi pn. And then another set of modes here, which I'll call phi fn. So notice that since these are complete sets of modes, this is, so the formulas for this are, for example, phi fn is equal to phi plus quasi-normal, and there's b's on everybody, and also all their descendants, phi plus or minus phi plus quasi-normal b plus its complex conjugate. This is the simplest of them. Sometimes there are phases there. And we can also invert these formulas. So for example, phi plus b is equal to, so the formulas get a little more complicated here. It's equal to I over sine 2 pi h plus e to the minus I pi h plus psi phi fn b plus phi esb. Okay, so it's an invertible transformation, and these are similar. However, what's interesting from this point of view is notice that the modes with S in them have absolutely no support in the northern patch, and the modes with north in them have absolutely no support in the southern patch. So these are kind of like the Rindler modes, and indeed Rindler modes are boost eigenstates, much like these are. And they're supported only in half the spacetime. So if all 4 of these is a complete set for the whole spacetime, but if I just want a complete set of modes for solutions in the southern diamond, I only need these 2. And similarly for the northern diamond, I only need these 2. And now I worked out the commutators. So now I take the standard Klein-Gordon inner product involving space like 3 slices, and I define field operators phi hat b fs by taking the Klein-Gordon inner product, just the standard one, bulk Klein-Gordon inner product of the wave function phi b fs with the bulk field operator. This is an operator. And this doesn't depend on X. This wave function depends on X. This depends on X, but these are integrated over the slice of the Klein-Gordon inner product. So this is now an operator in the theory, but it operates if only it's non-zero, has a non-zero effect only in these in those regions. And now we can compute the commutators, and we find that phi hat FSB, phi hat ESB A is equal to I times some NAB, where these are just SO41 group theory coefficients. In other words, if we have the inner product, Klein-Gordon inner commutator between two primaries, commutators between the descendants can just be computed with group theory. Okay, so now I've already started talking quantum stuff. And so now I can define quantum states. So let me define a state by phi hat FSB 0P, sorry, 0F is equal to phi hat F north B 0F is equal to 0. So I have states which were annihilated by these operators and these operators. And I can similarly define an alternate state, phi hat Fs F north. No. P north, PS 0P is equal to phi hat P north 0P is equal to 0. Now, since there's an I here, we should think of 0P and 0F as like zero momentum and zero position states. So the normalization would be like 0F. We can normalize them so that 0F, 0P is equal to 1. Okay, now I have this formula here. Now one can show that this quasi-normal mode and all its descendants are constructed from positive frequency modes with respect to global time. So the Euclidean vacuum is defined by phi plus Qn B 0 Euclidean is equal to 0. But that's a linear combination of these basic operators, the southern and the northern operators. So, so we see now we have two Hilbert spaces here. The Hilbert space, we had a similar formula for the northern things. It's also equal to I and AB. So we have two copies of this, and we see that both the northern and the southern operators appear in here. So we can find a state that obeys this is going to be a quadratic exponential in these Rindler-like operators. And so we get the formula. And we find that the Euclidean vacuum can be written as E to the I, E to the I, H plus NAB phi hat A PS phi hat PN B acting on the vacuum 0F. And there's a similar formula for an alternate representation of the Euclidean vacuum built as the other kind of operators on 0P. So now each of these, so in the dual conformal field theory, three-dimensional conformal field theory, this is an operator that acts at this point on scribe plus, and it creates a tower of states which are in a representation of the conformal group of a three-dimensional CFT. So by the state operator correspondence, there's a one-to-one identification between all the states in the Fock space built by powers of phi A and its descendants with all the states of the three-dimensional CFT. But we've also got this phi hat P north, which lives over here. And so this object is not something which lives in the state of a single conformal field theory. Rather, it lives in the tensor product of the Hilbert space, two copies of the Hilbert space associated with that boundary conformal field theory. So this is an expression of the Euclidean vacuum. This can be interpreted in holographically as an expression for the Euclidean vacuum as a thermal field double in two copies of the dual CFT Hilbert space. Now we could trace over the density. We could, of course, trace over the northern modes, and we do that in the paper. And we find, as expected, if we trace over the southern modes, so if we take trace to the south of 0E, 0E, we get rho north, which is proportional to, as expected, e to the minus 2 pi, the static Hamiltonian, but that's equal to e to the minus 2 pi I L naught. So from the point of view of the 2D CFT, it's at a temperature, it's an imaginary temperature I over 2 pi. And that, of course, is related to the fact that L naught runs in a time-like direction in the static patch, but runs in a space-like direction in the dual CFT. So these are features which don't have analogs in ADS. Now, to clarify this a little more, let me write the bulk boundary reconstruction formula. So this is a formula. It's a little bit trivial, but it's the formula that tells you how, given the boundary CFT, states in the boundary C, how you reproduce bulk correlators. And it's simply the expansion, phi of x is equal to minus I NAB. And then we have phi A PS of x. This is a wave function times, this is an operator, phi hat FSB. And then, okay, so if you're careful about the minus signs, it turns out there's a minus sign here. So then we have minus phi A Fs of X, phi hat Fs, phi hat PS of B. And then we have two terms which involve northern modes, phi PNA of X, phi hat Fn B, and then minus phi hat Fn B minus phi times phi Pn of X minus plus, sorry, this was minus, once this plus, minus phi Fn A of X phi hat Pn B. I got one too many terms here. 1, 2, 3, 4. I wrote this last one twice. Okay. All right. So what's interesting about this formula, so these we can interpret as operators in the 3D CFT. They don't depend on X. They create states in the 3D CFT. And so you take operators in the 3D CFT and you multiply them by wave functions that depend on the bulk point X, and you combine them together in this way, and you get the four-dimensional field operator. And correlation functions of this four-dimensional field operator in this Euclidean vacuum that I just wrote down will reproduce all the ground state correlators of a free field theory in de Sitter space. But suppose we consider points, we consider some correlation function phi hat of X, phi hat of Y, where both points are in the southern diamond, southern patch. Then these two terms won't contribute. So that's telling us that a complete theory in the southern diamond, in the southern patch, requires only one copy of the CFT. So it says that one copy, the Hilbert space of one copy of the CFT can be identified with the Hilbert space of the static patch. But if we want to construct the whole global Hilbert space, we need two copies of the CFT. And then if we construct a state with appropriate thermal field double correlation between those two copies of the CFT, we can make one pure, fully de Sitter invariant state out of it. So that is how in DSCFT, a whole de Sitter universe arises from two copies of the Hilbert space of the dual conformal field theory. So that's 10 o'clock, and I will stop there.
Thank you very much for very great talk. Thank you very much. So it's a great. So it is a good time for questions. So if you have a question, please unmute and ask question. Yeah, anyway, let me start one question. So I saw that you have two boundaries. I mean, future boundary and past boundary. But actually, these two, each of them correspond to one Hilbert space. But this is not true. I think in your actually south pole and north pole actually gives an independent Hilbert space. Is this true?
Well, I mean, the states, you know, in ADS 4, the boundary is S2 cross R. And the boundaries don't live on, the states don't live on S2 cross R, they live on S2. They live on slices of the boundary. And so the same thing is true here. The states don't live on the S3s. They live on slices of the S3s, which are S2s. And also, even though these slices are at past or future infinity, we can still find bulk space-like slices which end on those space-like three-dimensional slices, R3 slices, which end on those S2s. And so that's the picture I was drawing earlier. You have a state which ends on a slice there, a bulk state which ends on a slice there. And if we blow this, let me blow this picture up. I think it's useful to blow this picture up. So this would be an S3. And before we start talking about states, we could have correlation functions which corresponds to operator insertions at various places at points. But now, if we, this is the boundary picture of what I was saying before. Now, if we have a slice that ends there, that will be on N on some S2. Mm-hmm. And from the boundary point of view, we get two states on those S2. Right? We get this, we could ignore this.
Yes, it is.
And we could say, put these operator insertions in, do the path integral, and we get a state here. Or we could ignore this, we get that state too. We'd get the other state. So we get two states, and the whole partition function with insertions on that S3, it can be interpreted as the inner product between these two states.
I see.
So S3s are not one state, they're like two states.
Yes, I see. Also, can we understand this Dojita entropy from this kind of structure, tensor product structure?
Well, yeah. So I didn't mention this. I'm glad you asked that. Of course, let me first say it's obvious that the de Sitter entropy has to be the Ryu-Takanagi surface at the bifurcation point. But one would like to have some theory of Ryu-Takanagi surfaces in de Sitter space, which is sorely lacking, from which one could derive that statement that I just made. There must be some. I don't think we need a microscopic theory to see why that should be true. And that's one thing that, and I think some of your ideas about that your group has been developing about pseudo entropy and so on should be relevant for that. But remember, at some point, I constructed a row. And I understood that as an e to the 2 pi I L naught in the CFT3. So I can now make a partition. Will there be some normalization factors? So now I could make the entropy rho log rho using this, and it gives me a it just becomes a standard CFT3 entropy. So that tells me that it tells me that the entropy is a well, the partition function, entropy can be derived with the standard formula from the partition function of the CFT3. In this case, since I'm in 3+1 dimensions, this will be a partition function on S2 cross S1, but of the CFT3, however, at imaginary temperature. Now, the fact that the temperature is imaginary, has eyes in it, but the typical field theories, dual field theories, also have funny eyes in them. So, so there's some work there to understanding how these eyes turn out. And it's saying that it's an ET, it's saying that there's an eye here means that you're doing it at a Lorentzian torus. But working on a Lorentzian torus is for a field theory where for 3D field theory with imaginary in a quasi-normal mode basis may be the same as the Euclidean torus. I haven't understood that. But it does, however, I think, from my way of looking at it, give a first sort of starting derivation of what the entropy is in the dual CFT3. And there's a paper long ago that I wrote with Raphael Uso and Alex Maloney, maybe 20 years ago, in which we looked at Schwarzschild, Kerr-Schwarzschild DS3. And in that case, you have a full conformal 2D conformal field theory instead of a 3D conformal field theory. And there we derived some formulas for this partition function. At that point, we had no motivation for saying that the partition function of the conformal field theory, we didn't understand the things, we didn't understand this thermal field double stuff. We didn't have any motivation for saying that the 3D, that the entropy was somehow related to the partition function of the dual conformal field theory. But now we do have that motivation. And we noted just numerologically using the Carty formula, which can't be justified in this context, that you got the answer you wanted for the entropy for the macroscopic answer for the entropy of Schwarzschild Kerr de Sitter. So, so some more pieces are falling into place here, and maybe there's some way of making this more rigorous. So yes, now I think it is a possibility that the de Sitter entropy could be microscopically computed from some kind of calculation of a partition function in the boundary field theory. And perhaps your pseudo entropy is going to provide a more systematic. You guys also have funny eyes appearing, which you have to keep. I think I saw this e to the 2 pi I L naught in one of your papers there. So in a not unrelated context.
I see. Yeah, that's very interesting. Okay, so any other question? Yes, please.
Hi, Andy.
Hi.
Hi. I have some related questions about this expression.
Yes.
So when you write out this expression, the generator L0, is that a Hermitian generator or anti-Hermitian, or like neither is the case?
Okay, so let's step back a little before we start talking about, well, just in the bulk. So what you would usually do in the bulk is the most standard treatment, you would go to the global modes. You'd start with spherical harmonics, and then you would solve the wave equation. You would find there would be two solutions that depend in some complicated way on time. Hypergeometric functions, I think, in general. And then you would find, in a rather complicated way, some linear combinations that were positive frequency, and those would define the Euclidean vacuum. And in that context, the generator of time translations is the spectrum. The spectrum of L0 would be, the spectrum of H, the static time translations, would be Hermitian. Things would be oscillating.
Yeah.
The modes are oscillating in time. Now, the quasi-normal modes, of course, don't oscillate. They decay or grow. And it's kind of a surprise. Now, obviously, then the eigenvalues of H are not going to be real. They're going to be imaginary. So the Hamiltonian, which was Hermitian in the usual basis, is not Hermitian in the quasi-normal basis, because the eigenvalues, the frequencies are imaginary.
So,
but it's still a complete basis. So we have to understand better what it means. It's not only a complete basis. I guess I tried to argue here that at least for some purposes, it's a much more natural basis for thinking about de Sitter space. It's also a more natural basis for thinking about a lot of aspects of black hole physics. People who study perturbations of black holes also want to use a quasi-normal, quasi-normal mode basis. So it's a space on which the Hamiltonian does not act in a Hermitian manner. These L naughts in the quasi-normal basis are real, so H becomes anti-Hermitian, I guess.
So in that
Or it
sense,
has imaginary eigenvalues anyway. Let me leave it at that.
like H static has imaginary eigenvalues, right?
H static has an imaginary eigenvalues. That is the definition of a quasi-normal mode.
I see. So in this case, this L naught has real eigenvalues.
L naught has real eigenvalues in the mass range that we discussed. Yeah.
Yeah. So in that sense, it really looks like some kind of like maximally entangled state, because like all the spectrum, all the absolute value of exponential to 2 pi I L0 is just 1.
Right. And a lot of people have been talking about maximally the vacuum in de Sitter space is maximally entangled.
I see.
Witten wrote a paper on this, and people have followed up on that. And this could well be connected in some way.
Yeah.
But we haven't made it. We haven't made it concrete.
I see. Thanks for your comments. Thank you.
As a question?
Okay, then can I have a question? Okay, yeah. Thank you for the nice talk. And yeah, first of I just want to confirm. So by quasi-normal, so are you imposing the boundary? First consider the field in the static part, and then considering the ingoing boundary condition along the horizon?
No, we didn't impose any boundary conditions you could say it this way, before I went to the FNPS, the original quasi-normal mode basis, which were generically non-vanishing everywhere, you could say that the phi plus and the phi minus modes obey different sort of, but it's a little subtle to explain exactly what they do, but they obey different boundary conditions at past and future null infinity. And they're kind of like Dirichlet versus Neumann. You don't want to use both of them. That would be over complete. Now, we didn't impose. What we did was we tried to find a linear combination of these modes in order that we could say which of these operators. We had two CFTs. We wanted to divide the modes into the corresponding modes into the fields operators to the ones that are dual to operators in the northern CFT and ones that are dual to operators in the southern CFT. And for that purpose, it was convenient to explicitly write modes which vanished either in the south or the north. So we just took linear combinations. Now you could ask the question, I mean, I haven't looked at this explicitly, but you could ask the question, what kind of fluxes do these have across these patches? And I think that none of them have any fluxes because they're all real. And it's also true that if you took an incoming mode and took its real or its imaginary part, it wouldn't have any fluxes. The fluxes are off diagonals. The things that have Klein-Gordon inner products, nothing has a Klein-Gordon inner product with itself. It has Klein-Gordon inner products with its partners. So we've rearranged the basis in a somewhat different way.
Mm-hmm. I see. Yeah. Since so we are for example, in ADS case, so we are imposing the some Dirichlet boundary condition in ADS boundary and ingoing boundary condition in the black hole horizon to calculate the quasi normal modes in ADS using ADS CFT. So yeah, I just wonder whether we are also doing the same thing in static patch here.
You mean before? Or you mean the original quasi-normal modes?
I think which is near to the pole of the
original quasi-normal modes. Yeah, they're defined in the usual way that quasi-normal modes would be defined. They have. Yeah, they have. Yeah, if I remember this. So for the original quasi-normal modes were complex. They do have Klein-Gordon fluxes. And I think they decay exponentially as you go up to there, and they have no flux coming in here. But again, there's kind of an off-diagonal structure because the Klein-Gordon inner product will tend to be between the quasi-normal modes and the anti-quasi-normal modes. Quasi-normal modes, yeah.
I see. So here, so the boundary condition is different from that one, maybe.
And I think we're using completely the standard boundary conditions for the definition of quasi-normal modes.
I see. And another question is, so does this argument depend on the dimension of the Toshita space? I feel so you are.
No,
basically-
I'm just partial to 4 dimensions. I like to give explicit numbers rather than say D and D minus 1. So, and I always use 4 dimensions as an example. But no, this works in any number of dimensions.
I see. I see. Okay. Yeah. Thank you.
So I'd like to suggest close this colloquium, but we continue a discussion session. Andy, do you have still some time?
Yeah, I have time.
Yeah. So anyway, let us close. So thank you very much for really wonderful talk. Let us thank Andy for
My pleasure. Thanks
Thank you very much.
for having me.
So yeah, okay. So let's